What's up, everyone? This is LeetCode 191, number of 1 bits. We've done this problem in Python, but now we're doing it in C++. So we have to write a function that takes a binary representation of a positive integer and returns a number of set bits, which refers to a bit in the binary representation of a number that has a value of 1, also known as the Hamming weight. So for example, we have an integer, right, 11. The binary representation of 11 is this right here. And as you can see, we have 3 1s, right? 3 1 bits, so we have to return 3. Integer 128, this is a binary representation. There's only one bit, so we return 1. This number right here, the binary representation is this, and we have 31 bits. Okay, so the problem isn't too difficult. I think the only difficult part in terms of how you might approach this is kind of the more optimal solution that's a little bit tricky. But like, let's just think through this logically. If we have a binary representation like this, how do we count the number of 1 bits, right? Well, we can AND it with 1, right? So we have something like this, right? We can AND this with 1, right? And if our result is 1, we know that this number is a 1, right? So we can have a counter that we increase along the way, right? So when we AND this last bit with 1, we get 1, so we know that this number is a 1. So we increase our count by 1, right? And we right shift, right, by 1. Then we do the same process, right? AND it by 1, we get a 1, so our counter goes up by 1. Right shift by 1. Now when we add this and this last bit by 1, we actually don't get 1, we get 0, right? Because 0 and 1 gives you 0. So we know that this is not a 1. Okay, so we don't do anything to the counter, we keep right shifting. We AND this last bit by 1, we get 1, so count goes up by 3. Goes up to 3. Then we right shift again, and of course we get 0, 0, 0, 0. So because this number is now 0, we can stop checking and doing any ANDing operations. So at this point, we just return count, which is 3, which is what we should get, right? So yeah, that is one solution. It's not the most optimal, and I'll show you why, right, in a little bit. So we're going to set the count. We're going to say, while AND is not equal to 0, I'm going to do something. Okay, so we're going to say if AND n and 1. So we have some number n, AND it by 1 to get, so basically AND the last bit by 1, right? If that's equal to 1, then we can just, not return, sorry, we would increase our counter, okay? So increase the counter by 1. Nice. Now, regardless of whether we regardless of n and 1, whether that's 1 or 0, we're going to have to right shift, right? So we're going to right shift by 1, okay? Now, when we exit this while loop, n is going to be 0, so that's where we would return the count, okay? So yeah, I mean, this approach is simple in terms of what you're doing. So if it's not simple to you, you probably should just brush up on your binary operations. This isn't too difficult what we're doing, but the issue with this solution, though, is we're checking every bit, right? There is a way, like, why are we checking this bit, for example, if it's not 1, right? And so that's where we run into problems, okay? So there is a solution where we only consider the bits that are 1 and we count them, right, without counting these. And really, the idea, right, in terms of the optimal approach, I think it's better I draw it out in a comment just so it's a little bit easier, okay? But really, you have some number, right? And basically, you have some number and you AND it by n. You have some number n and you AND n by n minus 1. And in that way, you're basically counting, quote unquote counting, or I should say handling the bit that is 1 on the rightmost. Okay, so for example, this is our n, right? And when we AND n by n minus 1, this is our result. Now, as you can see, this bit, it gets removed, right? And we're left with this. just as, so we have 1 1 0 1. Up here we have 1 1 0 1, but we handle this bit, right? So this is our result. So we basically handle this one, so we increase our count, right? Now this is our result, and this result is actually 104. Okay. So this is our new n. So we have to do n and then AND that with n minus 1. So we have 104, and we have to AND that by 103. And this is what we have, and we have to AND it by this. And as you can see, right, we have 0 0. We have 1 1 0 1. This 1 is going to disappear, right? Because we're going to handle it. As you can see, this is our result, right? These first two ones are still here, but this third one now is gone. So we handled the second one. Okay. Now, so this is our result, right? And this result is actually 96. You can check in a calculator, a binary to decimal calculator, but I've done this already, so I know that this is 96. So anyways, so we have this number here, which is 96, and so this is our new n, and we have to AND n by n minus 1, so n, and then we AND that with n minus 1, which is 95, so we have to AND this binary representation here by this, and we're going to handle this one now, right? So we AND this by this, and we get this, which makes sense, right? Because this 1 here, we have a 0 here, so that's going to be 0, right? We're going to essentially remove this 1, okay? So every time we do these operations, we're adding 1 to the count. Does that make sense, right? Because, for example, here, this is our original number, right? We're going to handle this 1, and now in our result, it's no longer there, so we increase the count by 1. So now we have 3 1s instead of 4. Here, we're going to handle this 1. As you can see, we handled it, right? So now our count is up by 2. Here, we're going to handle this 1, right? And we do. This is our result when we AND n by n minus 1, right? We AND n and n minus 1, right? Meaning, what I mean by that, in case you're confused, is we're just doing this, okay? That's all we're doing, okay? This is what I mean. So this is our result. We have one more one to handle, right? And so we and this number right here is 64, right? So we do 64, and then we AND that by n minus 1, which is of course 63, and we handle this final one, and now it's all 0, right? And of course we increase our count, and it's 4. So as you can see, we really did 4 comparisons, right? We did 1, 2, 3, 4. Okay. Now, why is this good, right? Is because we only did 4 operations to handle these 4 ones here. This one here, this one here, this one here, right? Now, obviously, this has more than 4 bits, right? But we only handle the 4 bits that are most relevant, which are the ones, right? That's why this solution is optimal. Because if I showed you that first solution I showed you, where we check the last bit, if we did that, how many times would we be checking, right? We'd do 1, 2, 3, 4, 5, 6, 7. We would basically do 7 checks and 7 operations, right? Ending the last bit by 1. But in this solution, this optimal solution, we're only checking 4 times because we only care about the ones, right? And this idea of ANDing n by n minus 1 makes it so that we basically handle the 1 bit on the rightmost one, meaning we handle the 1 bits from right to left, okay? That's why this solution is optimal, okay? Does that make sense? So rather than checking n, let's say we have a binary representation with n bits, rather than checking all n bits, right? If we have 7 bits, rather than checking all 7 bits if they're 1s or 0s, we do this optimal approach, and we only handle the number of 1s in the actual binary representation, right? We only handle the 1s rather than all the bits. That's why it's more optimal, okay? It's a pretty clever solution. I'll be honest, I couldn't come up with this on my own when I first came to this problem, so don't feel bad if you can't. It's a little bit tricky, but it is really clever, and it's something that you can use in the future, right? So just add it to your toolbox, so to speak. But it is a really clever solution. It's really neat to understand and see how it works. So yeah, That's the optimal solution. Again, like some of these optimal solutions on LeetCode are not that obvious. So like the first solution I showed you, which isn't the most optimal, that's a little bit obvious, but this second one that's optimal, right? Like the follow-up, how would you optimize it? That's not too obvious. At least it wasn't to me, okay? But don't feel bad, right? Just learn it and yeah, you'll be fine. So we're gonna say while n is greater than 0, right? Because basically we want to keep doing these operations while n is greater than 0. Or you can say n is not equal to 0, whatever, it doesn't matter. I'm just right, you can say this. I'm just gonna say this, so same thing. So we're gonna say n is equal to n and that by n minus 1, right? Because when we and n minus 1, we're gonna get some resulting binary representation. That's our new number, right? That's why we have to set that to n. And every time we do this operation, we're taking away a 1 from the rightmost one, right? So we have to increase the count because we're handling some bit that is set to 1 every time we do this operation, okay? So we're going to keep doing that while n is greater than 0. At the very end, boom, we can just return count. Oh, I forgot my semicolon. But yeah, that's the optimal solution. I'll put this comments up again. Give me a second, just so you can review if you want to. You can pause. But yeah, this is the optimal solution, and this is essentially like a visualization of how it works, okay? Where the input string is 108, okay? Again, it's a little bit tricky to come up with on your own, so don't feel too bad, but, you know, just learn it. It's really not that difficult to understand what this code is doing, and you can use it in the future. So I hope this helped, and I'll see you in the next one.